Hello, welcome back. My name is Haulana Matamanaisha, and I'm here to give us a walkthrough in our project, which is a semantic-aware multimodal data warehouse for crowdsourcing and contextualizing AI-generated education content in fragile contexts. So the main problem we're addressing here is that the current educational systems struggle to generate culturally grounded, and relevant educational content, especially for low-resource environments like refugee camps and all. So our solution combines a multimodal data warehouse, knowledge graphs, semantic retrieval, and multimodal agents to generate localized and competence-based educational content for such environments. So we're under the Department of Computer Science, Makerere University. We are a team. We are a team of three: me, Sukwe, and Edgar. So moving on to the introduction, let me start by explaining the keywords of our project. So a semantic data warehouse, this is one that is enhanced with meaning and relationships between the data and the metadata, the ontologies, and the semantic models. So when you're using such a warehouse, it helps the systems to understand the data context and improve querying, integration, as well as the analytics. Then crowdsourcing. So this is a practice that combines like obtaining ideas, services, data or solutions from a large group of people, usually through the internet. For example, it could be done in surveys, open source projects, and platforms like Wikipedia. And then fragile context. So fragile context, these are situations where small changes in input, environment, or assumptions can cause like a misunderstanding or a failure in the system, especially in communication and AI systems. And then so multimodal AI. So these are AI systems that can process and combine multiple forms of data. For example, text, audio, and image. So they have multiple inputs like to generate smart outputs. And then knowledge graphs. So these are structured networks of connected information showing relationships between entities and like they're connected concepts, structured relationships. And for in our project, we're using them for like curriculum mapping and semantic reasoning. So we have like a concept, topic, then skill. So so for our project, just a moment. So for refugee learners and other learners in fragile context, as we had said, most of the material that exists is text-based, and it is really not relevant for their setting that they are in. So that was this problem led to the development of our semantic-aware data warehouse. This is like for us to be able to like to help the models, the generative models, to like produce content that is pedagogically aligned and relevant to such an environment. Yes, so there was a need for structured context-aware data systems. That was like a major problem. So we went on to review related works to the work we were doing. And so here in this section, we reviewed existing work related to multi-agent systems, retrieval augmented generation, knowledge graphs, and multimodal educational AI. So we started off with a Mac SQL. This in here, they demonstrated a strong multi-agent reasoning for like SQL tasks, but then it's mainly focused on structured querying environments rather than educational generation. And then we looked at the structure. So this in here, there was improved reasoning using the structure-aware retrieval, but it depended heavily on predefined schemas that lacked adaptation for fragile educational context. And then the GenMentor, so this focused on like personalized tutoring agents, but it did not address the semantic infrastructure or knowledge validation. And then we looked at the traditional RAG systems. There was improved factual grounding, but they treated the knowledge largely as unstructured, text-based, and this lacked contextual educational alignment. And then the knowledge graph-based systems, this improved in the semantic linking between like the semantic linking, but however, they faced the scalability challenges in low-resource environments. So I would say overall, the existing systems lacked semantic educational grounding, multimodal integration, cultural contextualization, and epistemic trust mechanisms. So what's our work? So this brings in like a novelty of our work. So because we attempt to bridge these gaps through a semantic-aware multimodal data warehouse that is integrated with graph constraint AI generation. So our research was guided by like a few questions and objectives. So our objectives were, we majorly had 4 goals. So first, we had to enable textual contextualization of educational content using like LLM, large language models. Then secondly, we have to enable visual contextualization through image and video grounding. Then third, to ensure alignment to the competence-based curriculum frameworks. And then lastly, to design a scalable semantic-aware data warehouse architecture, which is suitable for deployment across multiple regions. For example, across our research is also guided by 4 questions, and which are designed to evaluate contextual coverage and semantic competences. So, for example, which curriculum competences are like have contextualized examples, and then which regions are well represented and which ones are underrepresented, and then uploads producing complete semantic descriptions and tags, and then how many contextualized lessons has a teacher generated. And then so for what we've done so far, these are some of our contributions. So first, so these are some of our contributions, which was we proposed a semantic-aware multimodal data warehouse and architecture system for education AI systems, and then it was based on like it was an offline fast semantic ingestion pipeline, and then neurosymbolic agent educational grounding framework, and then semantic business intelligence, as well as proven traceability prototype, Java prototype. And then so I would say these contributions like advance the trustworthy and culturally contextualized educational AI. So moving on to the computational. Just a moment. So moving on to the methodology. So we have our methodology. This max it was mainly a multimodal a multimodal semantic engineering approach. So in here, the process begins with like the process here we start with the process begins with like local multimedia uploads, including images and videos from a refugee community. So like we take images and videos of like the whole environment and how everything is set up. And then so these artifacts are then stored in a Supabase bucket storage. Then the uploaded media is then analyzed using the vision language models. So to extract the semantic descriptions, the environmental tags, the culture indicators, and the material references. Then this extracted metadata is then embedded into a vector representation and linked into the Neo4j knowledge graph. So the graph structure then enables the semantic retrieval of the culturally relevant educational evidence. Then finally, the retrieved evidence is used to generate localized competence-based lessons aligned with the Ugandan curriculum. So this creates an end-to-end pipeline from like the community media collection to from the community media collection to the grounded educational generation. And so talking about moving on to the computational problem. So the core computation problem, the challenge is not simply content generation. Here, the problem involves like grounding the AI-generated educational content using weakly supervised crowdsourced multimedia evidence under strict pedagogical and cultural constraints. So our system must process highly unstructured multimodal data that is multimodal data like to align content with the competence-based curriculum standards. And then we must be able to avoid and prevent hallucinations and then maintain the culture sensitivity. So this is like very, very important. And then it must continuously learn from the community contributed media. So to solve this, we designed a decentralized architecture where edge devices collect media that is synchronized into a cloud-based semantic warehouse. Then the generation process uses like a neurosymbolic multi-agent architecture where LLMs and vision language models are constrained using graph-based symbolic logic. So moving on to the data set and the knowledge graph description. So our multimodal dataset composition. So in here, like we're talking about the multimodal dataset composition, the semantic knowledge graph, and the infrastructure used to organize and contextualize the education artifacts. So our dataset has it consists of like crowdsourced educational media collected from low resource and refugee learning environments, refugee communities. Then we have consists of like multiple modalities that are incorporated. So in here we have videos, images, text, localized text, and curriculum documents, media artifacts that are uploaded through like the decentralized edge devices before synchronization with our multimodal with our warehouse. And then the semantic preprocessing is performed to reduce like noisy and structured inputs into like machine readable metadata. And so this table is just like a summary description of the content of the warehouse. So we do have the curriculum corpus that we got from the NCDC, like the Ugandan NCDC website, the Ugandan curriculum sources, and this is just text. And then the uploaded media, this is what I was talking about, that is collected from edge devices, the videos, images, and texts. And then we have semantic annotation. So this is AI generated from the media, from the text and the tags. And then the graph records, these are derived warehouse entities. So in here, it's like an image showing like the semantic extraction process, like from the whole process. So we do have the curriculum source. So before the semantic extraction, like the uploaded media exists as highly unstructured visual and textual content. Then the vision language models transform these artifacts into like semantic descriptions and into semantic descriptions and contextual captions and semantic tags. Then the semantic tags represents like the environmental context, the cultural activities, and the local materials and the learning relevance. And then from in here, we move on to like the knowledge graph organization. So then these extracted entities are then mapped into a Neo4j knowledge graph. So each education artifact in here becomes a semantic node connected through like relationships such as like the regional alignment, curriculum, competence linkage, and contextual similarity. The graph structure, it enables semantic reasoning and contextual retrieval across the heterogeneous educational content. So the importances of our semantic warehouse. So the traditional relation databases, these ones struggle to model highly and interconnected multimodal educational relationships. However, the semantic knowledge graph allows dynamic linkage between the curriculum standards, the community knowledge, and the multimedia educational evidence. So I would say our semantic data warehouse therefore transforms the fragmented crowdsourced educational data media into an interconnected and searchable epistemic infrastructure for grounded AI educational generation. So moving on to our models and the mathematical formulation. So at this stage, I represent the AI models and the mathematical foundations governing the semantic extraction, retrieval, and contextualized lesson generation. Starting off with the vision language model, the VLM. The vision language models are utilized. We use these with the MetaLlama. The MetaLlama instructs the Grok here to analyze the uploaded images and the sampled video frames. So, like we analyze the uploaded image and the image frames, and then the model then generates descriptive captions, semantic tags, contextual metadata. So this would in turn like enable multimodal understanding of localized education artifacts. And then the transformer-based generation. So large language models are used for contextualized lesson generation. For example, semantic organization and the curriculum alignment, retrieve semantic evidence. All these are injected into prompts to constrain generation and reduce on the hallucinations. And then we move on to like the dense embedding model for the semantic retrieval. So here we used fast embed with mini LM embeddings. They were used to map like the curriculum content, the semantic descriptions, and user queries into a shared vector space. Then semantic similarity search identifies the most contextually relevant educational evidence. Then for the mathematical formalization, so the embedding function, it mathematically transforms the curriculum and multimedia data into dense vector representation. And then the retrieval functions compute the semantic similarity between the queries and education artifacts. Then the region constrained retrieval, it ensures generated education content remains geographically and culturally grounded. And then for the autoregressive generation, in here, like the lesson generation follows an autoregressive probabilistic modeling objective. So the next generated token is conditioned on the following, it is conditioned on the retrieved semantic evidence, the prior generated tokens, and the curriculum context. So this would strengthen the factual consistency and the pedagogical validity. So the mathematical formalization, therefore, it was used to establish the computational foundations. This is to enable like the trustworthy semantic retrieval and grounded educational generation. So just a moment. And then just a moment. So the business intelligence and traceability evidence generation. So in here, we like conceptualize the business intelligence as semantic traceability and evidence generation interface rather than like the traditional dashboard system. So our BI concept, it was like the BI layer functions as an epistemic auditing interface for AI generated educational content. So instead of like having static charts, the system performs like semantic content-based retrieval. And then users can inspect the exact curriculum competency, the multimedia evidence, and the graph substructures used around the AI-generated lessons. So this enables verifiable education evidence generation. And then for the semantic retrieval, the queries are resolved through the knowledge graph traversal, the vector retrieval, and the semantic similarity matching. The retrieved evidence is transparently linked into the generated outputs. For the educational governance, the teachers and the curriculum auditors can validate whether the educational content like is authentic, like with respect to the cultural sensitivities, does it align with the CBC standards, and does it reflect like local realities? So the semantic BI layer therefore establishes like explainability, accountability, and the epistemic trust with the AI-assisted educational content. So, so moving on to just a moment. So, so moving on to the evaluation, benchmarking, and governance results. So, for starting with like in here, we present like the evaluation methodology, the benchmarking strategy, and the governance considerations is to assess the semantic extraction and the generation robustness. So starting off with the semantic extraction evaluation. So our vision language model outputs, the outputs of the vision language models are like evaluated against human expert annotations, and then the performance is measured using precision and recall. And then like we look at the ability of the system to identify local artifacts and cultural idioms. Then we test it like across different environmental noise and the camera qualities. And then moving on to the already generative robustness, like out of distribution robustness. So we do have like random train test splits. We avoided like to prevent the data leakage, and then like our architecture, like we utilize like region held out evaluation like to assess the generalization across the different refugee environments. And then so it helps us to evaluate like whether the system can adapt to unseen cultural environmental contexts. And then moving on to the governance and the epistemic trust. So in here, so the knowledge graph in here, like so the knowledge graph grounding questions questions the AI system to like the retrieved semantic evidence. So it introduces like the hallucinations and the bias regeneration inherited from the pre-training data. And then the provenance tracking, it enables like verification of all the generated educational outputs. And then moving on to like the data ops, the deployment, and the edge orchestration. So so the evaluation so in here we present how present the distributed deployment of the architecture and the data ops orchestration strategy supporting the semantic warehousing and the constrained environments. So first of all, we looked at an offline fast deployment. The system is designed for offline. It was majorly designed like for offline fast operations, since like low resource environments usually have issues with like connectivity, and also we want edge devices to locally process the multimedia artifacts before like synchronization, and then the edge preprocessing. So here we use like the OpenCV processing and semantic compression to reduce like the bandwidth usage. And then we had the local vector caching to prevent like repeated semantic computations and reduce on the memory exhaustion. And then how we handle the synchronization pipeline. So we use the batch synchronization. It was used like it is utilized when the connectivity becomes available. So it enables decentralized semantic ingestion across the geographically distributed settlements. And then the orchestration logic. So the semantic extraction pipelines coordinate the VLM processing, the vector embedding, the graph insertion, and the semantic validation. So then the schema constraint generation ensures like that we have structured outputs. And then for governance, so And the metadata tagging and the provenance preservation occur before like the cloud synchronizations. This is to help us. This just a moment. This is to like strengthen the auditability and the epistemic traceability of the generated content. So the deployment architecture, it enables scalable semantic warehousing despite of the severe connectivity and infrastructure limitations. And then moving on to the limitations and the architectural failures of the system. So, so the major architecture risks and the failure modes associated with the multimodal data warehouse educational system. So first of all, cultural misinterpretation. So the vision language models may incorrectly interpret the localized culture artifacts or practices. And the semantic extraction errors may propagate through the knowledge graph and affect the educational generation. And then the graph sparsity problem. So the new deployment regions may initially lack sufficient semantic edges. And then the sparse graph connectivity can weaken the retrieval quality and the contextual grounding. And then we could also have like connectivity constraints, crowdsourcing, high resolution multimedia artifacts, and intermittent 2G and 3G connectivity. So these limitations demonstrate like as I was saying, the delayed synchronization may also reduce like the semantic freshness. And and then so so as I was saying earlier, that the limitations like could demonstrate that the semantic AI infrastructures must continuously balance the contextual richness and the governance. Then moving on to our conclusions on the future works. So our research demonstrates that the traditional relational databases are insufficient for highly interconnected multimodal education ecosystems. And then the crowdsourced communities, the crowdsourced community media like the curriculum standards, AI-generated pipelines, and the architecture establishes like a contextual grounding, epistemic trust, and culturally relative educational content generation. And so in here, our future work will focus on deploying quantized lightweight vision language models directly onto mobile devices used for crowdsourcing entitlements, and then pushing the semantic extraction and validation of the offline edge. We can bypass the cloud bandwidth and constraints. And so thank you so much. These are our references, and we are the different things, the different papers we referred to when we were coming up with our work, and we would love to thank our